well as add the project description. So don't think that there won't be a project, there will be. I just have to add that still. Right, something else I had to mention, but I can't remember what. Oh, the actual names, your full name in Slack. Please do add that. I want to add you to the different groups, which are locked groups, and I need to type that in manually. If your name is only your preferred name on Slack, then I don't know who you are, and then I can't find you on the ClickUp page, so that I can't link the correct person. I mean, there are about 700 people that are on the CPN CPB group on Slack, so if I type in a name, there are more than one hit, and I can't find, I don't know which one is the correct one. So please do update your full name so that it reflects the ClickUp name, so that there's no ambiguity toward that. Okay, so let's start this lecture. First lecture of the CPN. Before we do that, Slack, a few other comments. Please make sure that you join all of these relevant groups that you see on the left-hand side. Obviously, the CPB ones aren't necessary now. I will create the groups for you that you are randomly assigned to. But please do join general, hashtag general, material request, project, random, and quizzes might be used this semester, might not. So please make sure that you join those various channels so that we can communicate with one another. The lecture schedule. Okay, I can explain that quickly. Let me just get that on screen. Right, so the lecture schedule that have been uploaded, you'll see that it's only the first portion that I uploaded. I'm still working on the rest. These are based on old stuff. So the first number, just starting week, obviously that starts on a Sunday, ISO kind of week dates. The number at the top represents the study theme for the lecture periods. And then there's some information on the tutorial session that is also scheduled on a Tuesday. The number at the bottom represents the work from Seborg 4th edition. So, this is what happens when you do work late at night. So I'm not going to handle too much about 2.2 today. But yeah, we'll catch that up tomorrow. But yeah, this represents the chapter in Seborg that you need to at least read through before the lecture. As I mentioned yesterday, I want to introduce the quizzes, or kind of just like a short multiple choice kind of assessment before the lecture, so that you are sure that you focus on the correct stuff from that section. The simulation notebooks obviously refer to additional notes and content that we'll discuss at that point in time. That still needs to be uploaded. Right, later on in the semester, you'll also see that things like Spring Day and public holidays are noted. Recess, this I think has been updated, but I'll indicate that later on when there's more information about that. Good. Yes, I haven't updated everything yet, so it'll be right soon enough. Recess is only 3 days. Yeah, I already started crying when I saw that for the first time. In any case, Seborg Chapter 1. I uploaded Chapter 1 and Chapter 2 under ClickUp additional material, something, pick up study material. please have a look at that. If you don't have the textbook yet, please get the textbook as soon as possible. I'm not going to upload everything onto ClickUp. That would be an infringement of copyright law. So we start off, process. What does that mean? A process is a conversion of feed material to products using chemical and or physical operations. So the word in our kind of industry refer to both the verb and the noun. Please don't stone me if my English is not perfect. I think it's a noun. Not really 100% sure. I'm not English. I'm Afrikaans speaking. But in any case, let's say it's a noun. The one refers to the actual physical processing. So what, the work we are doing. So we process food to make it sloppy stuff that you can drink, or we refer to a process as the physical equipment standing in front of you that does that processing of your food. So the blender or the food processor. And that is pretty much what we are dealing with in the entire. Let me just change my screens, otherwise you might be seeing all my notifications popping up throughout the lecture. Apologies for that. You should see my screen shortly. There you go. Okay. So now that we know what a process is, or at least have a fair understanding, please read through chapter 1. You can only read through, you'll kind of notice what I'm referring to in these short notes that I made. Please read through that. You don't have to understand everything in chapter 1. Basically just the introduction to what we need to know about dynamics and processes. So that would be 1.1, 1.2, a little bit of 1.2, and that's more or less it. Next, we have some important definitions that we must know, must understand, at least for the jargon that we are going to use in this semester. All processes that we control or controls itself has some form of a controlled variable. That is typically the thing that we want to keep constant, that we want to have a set point so that we have a profitable or exact quality of product or final item or stream that we want to control at. In order to do so, we need to manipulate something that can accommodate any other disturbances or changes in that process. And that we typically refer to as our manipulated variable. And then finally, all other variables that affect the process but cannot be manipulated, those we call disturbance variables. So when we refer to, and by the way, these notes are on ClickUp as well. Please don't include everything in there. You have to take some notes as well. So I'm not going to write everything down. It's there for your own handwritten notes that you can take more information in during a lecture. When we refer to a controlled variable, and please do not confuse this, I am sometimes going to use the acronym CV as a control valve as well, but in most instances it will be a controlled variable. And we typically, as I mentioned, control these so that we have some form of profitability for our plant. So we, as chemical engineers, obviously we take some crappy material and we process that into something that is refined and sparkly, and we can get a lot of dollars for that. We want money. As chemical engineers, we most of the time, except if you're an environmental engineer, you want to make money from whatever we are processing or doing. In order for us to make money, we obviously need to have some form of a quality for that product. So if we want a rectangular box, it can't look like this, because that is a poor quality product. We want a product that is on spec, always the right dimensions, always the right shape, always the right form. And in order to do so, we obviously need to control that at a specific set point. When we refer to a set point, that is obviously the position, or for that variable, the value that associates it with our final specification that we want. Sometimes our controlled variables aren't necessary for making money or ensuring the quality of the product, but also to ensure the safety of the plant and equipment. Not only the equipment, but also the personnel and the human inhabitants or animal inhabitants in the surrounding areas, so that we don't have a environmental disaster or loss of life or something like that around our processing plant or factory. Then we have our manipulated variables. So these are in most instances for chemical processes. We manipulate flows. So we manipulate the flow through a valve, or manipulate the valve, so that consequently manipulates the flow through that pipeline to increase or decrease the flow rate. And you'll see that a lot in the coming this semester and next semester, where we have something that looks like that. Is a control valve. There will be some lines drawn toward that indicates that we send a signal to that to make it open or close, so that we manipulate that flow. These flows that we manipulate are usually utilities. These utilities, I think I misspelled that, but that doesn't matter. Utilities are steam, cooling water, airflow to something, I don't know. Every now and then we might be manipulating the speed of a motor for a pump, let's say, or the number of rotations for something like a stepper motor to ensure that some linear actuation occurs, or we drive something left or right. So if we think about the everyday things that we have or that we know quite well, automobiles, there are a number of controlled, manipulated, and disturbance variables associated with that. In such a case, a manipulated variable would be your steering wheel or the brake pedal, where you manipulate a specific, I'm going to use the word variable, but you manipulate that variable in order for us to control some output. So the speed that we are going for, the direction that we're going in. And consequently, if I mention those two, like your petrol pedal or your diesel pedal or electricity pedal and brake pedal, as well as steering, then obviously we have a multiple input, multiple output system, because we now manipulate two variables and we end up controlling two variables, which is speed and direction. But more on that in the coming module CPB. Finally, disturbance variables. So disturbance variables are all the things that affect our process, but we cannot manipulate those. So sometimes you cannot manipulate a specific process stream because it comes from an upstream process, and that process uses that stream as a controlled variable, let's say. And if you now go and manipulate the downstream, you are changing their flow rates, their quality or something like that, and you are now causing major upsets and disturbances in the upstream process, and therefore we can't manipulate that stream, and hence it is a disturbance variable. Because at some point in time, that upstream process controlled variable will deviate due to some other disturbance variables that work or act upon that process. And therefore, that controlled variable deviating from the set point will now cause a disturbance in your process. Right, so hopefully you have some form of an idea what controlled, manipulated, and disturbance variables are. And we aren't too worried about what these means now, but from time to time you will come across these words, and you'll need to know what they are so that we can understand the questions that you are faced with. Right, Monique, you asked what, or an example of a disturbance variable. Let's use the example of the automobile. I'm not an artist, but there's our automobile, and we are moving in that direction. Now suddenly someone jumps in front of you and you need to deviate from your actual course. You want to go straight, but if you do that, you are going to hit a person that is frowned upon, and you need to deviate. So that person causes a disturbance in your required or your controlled variable path, the direction you want to go into, and you must deviate from that. So you have to go around the person so that you don't hit that person, and that has caused a disturbance which you change your manipulated variable for, so that you are A, avoid the person, and B, get back onto the correct path that you want to go to. In terms of a chemical process, as I mentioned, let's say we have this distillation column. This is our primary focus. It's a simplified drawing, so don't stone me for this, but this stream that I drew here comes from a plant that your colleague works on, which is some form of a reactor system, and he is responsible for controlling that. And that's the feed to your plant. Now, you may not change this process, and whenever his inputs change, there will be some up or down deviation in his output, which is an input to your system. You may not put a control valve there because it's you would cause upsets in his plant. So therefore, you cannot manipulate this stream, and that you must assume as a disturbance variable, which will affect both your, well, either both or one of them, either that stream or that stream after the distillation process has occurred. So that would be a disturbance variable in this simplified sketch. It is not necessarily totally internal. Remember, we are referring to a lot of simplified processes and sketches and so forth. You will obviously not be no, not necessarily. It's only predictable if you measure it. If you don't measure it, you don't know what's going to happen. Not all disturbances are measurable. Some are measurable, some aren't measurable. Whenever you get the feeling, or whenever you are faced with the question of list some disturbance variables, and we'll discover or handle some of these later on in the TUT today. Do not be tempted, or do not always be tempted, to refer to ambient conditions as a disturbance variable, by the way. They are really, or they really affect the process to such an extent that they are real, important disturbance variables to a process. To answer the other question, just want to get back to that one quickly. So Zander, that is what we handle in control. We will get to, I'll discuss this in some detail this afternoon before the TUT session. I'm not going to continue with that just now, but please remind me this afternoon, then we can discuss that. You may assume that, Alex. Sometimes engineers, or you don't even have to assume he's an engineer, but he might be an engineer from, let's say, NWU or something like that, and then we have to take all his decision making with a pinch of salt. I'm just joking. It's not a bad university, just terrible. Any Dievenage? No, do not. Again, we get to this in process control, but you can't always put a holding tank. Holding tank is an excellent way of kind of attenuating these disturbances. However, holding tanks cost money, a lot of it. So equipment is extremely expensive. You don't want to spend too much money on pretty much redundant or useless tanks that do absolutely nothing but attenuate disturbances. And that is actually where process control originated from. So back in the day, 40s, 50s, 1940s, 50s, they installed these sort of things because there weren't established process control methods and obviously no computerized systems that control these automatically. And you had to install a tank that acts as a buffer to that to any fluctuations or changes. But nowadays we have extremely advanced process control strategies, and hence we don't need those tanks. So we save on some capital equipment in terms of a tank, but we implement a control strategy that can take action in a matter of seconds perhaps, or maybe a minute or 2 or 3, depending on the dynamics of the system. All right, moving along. Okay, so you'll see this example in the textbook. We are going to refer to this example a number of times throughout the course as well as CPB. It is obviously the one that the textbook uses, but in any case, if you consider a blending system like this, we have 2 streams coming in. In chapter 1, x2 is constant at 1, so a fraction of 1, meaning it is complete whatever x is. And for us to be able to determine the dynamics and obviously the control eventually, we have to determine what the variables are, what we can assume to be constant, and we need to know what assumptions we need to make in order for us to be able to derive this dynamic model of the system. Apologies. We need to I lost track of where I was. We need to know what assumptions we can make such that we are able to determine this actual model of the system. And those assumptions are extremely important, because if you make the wrong assumptions, then obviously our model is not valid, and there will eventually be some fundamental flaw in the model that we develop, and all our simulations and so forth will be incorrect. Because we are going to refer to this process in 2.2 tomorrow, I'm not going to do it in full, but we obviously know, well, let's just reiterate the controlled variable, manipulated variable, and disturbance variables. And I'm going to ask you, let's say x2 equals 1 in this instance. What do you think, well, regardless of whether it's 1 or not, what do you think are the controlled variables in this blending system? Name 2. What do you think we would like to control? Okay, so Alex, that is correct. Marinique, unfortunately, you're incorrect. So Jordan, the question mark, if you answer a question like that in a semester test, that would be incorrect as well. So we see there, no, temperature is not even indicated on this. We are purely blending some stuff. Jordan, still incorrect. The S after rate mean it's incorrect because you want to control two things. You want to control the composition X and you want to control that flow rate W that's going out of the tank. So we have a tank, there's some capacity of fluctuation, so the volume most probably can change every now and then. It's an open tank as indicated in the diagram. Hence, we eventually, most probably, or the two most likely things that we want to control would be the composition going out, as well as that flow rate of that product stream. And we do that by manipulating one or both of our inputs, depending on what we can manipulate and depending on what we can't manipulate or measure. But in any case, so in this case, if this is a completely unspecified problem, then obviously all these inputs and outputs are variables. None of them would be constant, but this is so there are too many degrees of freedom. If we want to do that, we kind of have to decide which need to be manipulated variables so we can specify them. Otherwise, we won't have enough equations to solve it eventually. In any event, this is basically what we do in dynamics this semester. We take a process and we determine what our variables are. So we are going to jot them down. This is going to change. That's going to change. Let's say W1 is going to be a variable. And we are going to say that maybe X2 is a constant because that is equal to 1 and it will always be equal to 1. W2 is going to be a variable, and I'm just making these up as I go along. Not really, but in any case. And maybe X1 changes, just for the hell of it. So, from dynamic point of view, we are eventually going to have to write down some form of a differential equation so that we can fully define that problem, and we'll get to that shortly. I like these cliffhangers. Anywho, just something else that you need to know about block diagrams. From time to time, this will be thrown on your path, even in CPN. It's a convenient way of conveying information, but in any case, block diagrams typically include all our streams, our variables, and in this case, that what is presented here is a feedback control loop where we have some set point, which is compared to our measured variable, our measurement indicated there. That might be a temperature, it might be a flow rate, it might be a pressure, it might be something else. And that change or the difference between the two we denote as the error. That error goes through a controller, which is a computerized or software system, or could be actually mechanical, but more or less nowadays everything is pretty much computerized. That controller sends out some form of electronic or pneumatic signal to a valve or final control element, which manipulates some form of input to our process, so that we eventually mitigate that change, which is caused by either disturbance or a set point change. Alex, that is generally correct. There can be some instances where that where you manipulate an output in order to control your input. So if I draw this and we a control valve there, and we want to control the level. So we have a level transmitter, level controller. that's connected some inputs. Now you're manipulating an output in order to control a different variable. So it's not necessarily always an input that you are manipulating. Just be aware of that. But more on that in CPB, so do not be too concerned right now. Okay, so that is in a nutshell what you need to know from chapter 1. Please do read through that and ensure that you understand or get some background on controlled, manipulated, and disturbance variables. And for interest's sake, read through the rest of that chapter. It's not too long. And look at the examples that they provide there for different processes and so forth. Then, chapter 2. So our introduction to theoretical models of chemical processes. Obviously, we are chemical engineers, so we are mostly going to refer to chemical processes. And just after I said that, you will realize later this afternoon that that is not necessarily the case. But that's for you to find out a little later. Okay, so why do we need to know or understand the dynamics of a system? And if you think that this is the final answer, then unfortunately you're incorrect. We do assume steady state for pretty much all the things we try and do because we want to make it as easy as possible. But if we always do that and if we always work at steady state, then we will never actually need this module CPN 321, and we'll never be required to do CPB 410 because we will have a system that is at steady state. It's never going to change. So that is unfortunately incorrect, and we need to know the dynamics of a system for the following number of reasons. So firstly, we need to understand. That is a good answer. Good answer, Ivandre. Quickly read it, not 100% correct, but on the right track. So, in order for us to understand the process, we need to know how its dynamics work. For so simple example, let's say you want to know how hot your stove plate is. Obviously, if you have no idea what the dynamics of that is, you're going to burn your fingers and you're going to burn them a number of times because you don't understand what's going on. We know if we touch that hot stove plate, then there's some heat transfer going through the stove material, so that plate material, the metal surface, and that transfer is going into your fingers, so it's going through your skin. And if you keep your finger there for way too long, then you're going to burn it. So in order for us to understand that process, we need to kind of have an idea of how quickly it's going to happen. We have some form of an idea how hot that stove plate is. It's way hotter than our finger, or it can potentially be way hotter than the finger, so we need to be relatively fast in touching and removing it if you want to determine how hot that is. I have a weird and wacky sister-in-law, and she at some point in time tested the temperature of a, I think, hair curler or straightener or something on a lip, which is one of the more or less bright things I've ever heard of. But in any event, that's why we need to understand the dynamics of a system so that we can make an educated decision on how we want to or how we need to manipulate or change that process. Then the second one is for training. So if we have mathematical models, so obviously before we can train, we need to understand, and when we understand, we can derive these mathematical models, and when we have those, we can build computer programs, so simulations of these models, so that we can simulate various events that can occur on, let's say, a chemical process plant. And those events we can use to train personnel, so our operators, instead of giving them a process and say, hey, go and manipulate stuff and see what happens, which might cause an explosion and people might die. We would rather say, well, sit in front of this computer screen and change this knob and see if you can maintain that level or temperature by manipulating that knob. And we do that in a simulated environment so that they eventually understand, what's the cause and effect of their actions. So that's for training purposes. Then third, to control, obviously. So a lot of processing plants utilize feedback control systems. A feedback control system is something that waits for an upset to occur. And once that upset occurs, then only it takes action. So something must go wrong before you can take corrective action. However, there are other forms of control, so model-based control, model predictive control, as well as feed-forward control, and other fancy and weird stuff that a lot of people refer to as machine learning and things like that, which is sometimes used relatively incorrectly. In any case, for those sort of advanced methods of control, you require to understand and know the system. So you need some form of a mathematical model so that you can determine how an upset will change your process output before it occurs. So the moment you notice, so the flow is increasing, in about 10 minutes time, my tank is going to overflow, so I can take corrective action before that occurs. So even before the level increases in that tank. And that's why we need those models in control so that we can make informed decisions based on kind of a predictive control. Then lastly, not necessarily lastly, but the 4 points that is raised in the textbook is to optimize. As I mentioned right at the beginning, so our controlled variable, we have that usually, not usually, but sometimes for profit and for quality purposes. And obviously, if we have the most basic control system or most basic model, then you won't probably have the most profitable product. And in our in the cutthroat market nowadays, you need a product that is at the most optimized profit margin. So our optimization of our processes and models and understanding of these dynamic models enables us to increase our profitability. And I mean, there are a number of examples where a small change that saves a company a cent or two, maybe on a Coca-Cola can or something like that. Let's say you save 1 cent on a Coca-Cola can. Just imagine how much money you've saved that company over a number of years, where they produce 1 million or 2 million of those cans per day. It is eventually a lot of money, and that is purely due to optimization. And to enable optimization from a mathematical point of view, you obviously need the model. Right. So just so that we all know what this actually means. So if we look at the definition of dynamic, it's a process or system that's characterized by constant change, activity, or progress. And when we add that S, so not dynamic, but dynamics, dynamics is the study of that. So the study of, or the understanding of how that change occurs and how quickly it occurs. Now, when we refer to dynamics as in process dynamics, it is important to mention that we do need to know what the steady state, so our nominal conditions, are. It is not only about the rate of change, even though the word refers to that, But it's also important to know to what, where is it going to end? Because a lot of our modeling and conditions are based on the steady state conditions, so where it usually should be operated at. Okay, so please do not think that steady state is not important. We kind of have to do it like, oh, that looks like a butt. These two need to go together for us to understand or to enable us to do or build our models properly. So I did go through this in a decent amount of detail, but I haven't started this. So how do we get to the understanding or knowing the dynamics? We mentioned models. Models aren't those beautiful people walking on platforms showcasing the latest fashion. They're also models, but they are not as clever usually as the models that we are referring to. So firstly, we have theoretical models. We all know these. You've dealt with them. These models are governed by our conservation laws, so conservation of mass, conservation of energy, component balances, which is a, let's call it, subsection of conservation of mass. So the stuff that physically determines or governs our everything around us, pretty much. But there are always a number of pros and cons associated with these models. So in order for us to derive a theoretical model, if we take the blending system, which is just a tank with some inflows and one outflow, that is extremely easy. Given that we make correct assumptions, something like a continuously stirred tank reactor or something like that, or assume perfect mixing, then it makes it a lot easier. But not all processes are blending tanks. A lot of them are extremely advanced and complex, and therefore deriving these theoretical models do get extremely difficult, and it is extremely time consuming. And one bad assumption can cause that model eventually to fail or to deviate from the actual scenario. Another aspect about theoretical models is the non-linearity of those. So we'll trade on this in study theme 3 when we discuss non-linearity in more detail. But basically what it means, we, as you'll see in study theme 3, we kind of want to work with linear models, and in doing so, we end up simplifying around a specific point in our system, let's say our normal operating conditions. But if those operating conditions change, and they change substantially, then you end up at a point where you're so far away from the point of linearization that you see the effect of the nonlinear aspect of that physical, the real process. So yeah, we have theoretical models, but some of them do get so complex and it's so time consuming, which is obviously a cost implication, that it is not always practical to work from theoretical models, so from first principles. This is, however, the only thing that we'll be discussing in CPN. Not the only thing, we'll do some empirical models, I think, later on, but the majority of the work will be from first principles on relatively simple processes. But please do keep in mind that this is rarely the most practical case. Then obviously empirical models. Empirical models are those models that come from our experiences. So if we have some plant data available, then we can build an empirical model from that data. So we fit some form of a equation, let's call it a first order equation, to our plant data and say, well, we see that this roughly fits, is 1% accurate or something like that, or 99% accurate, and we work with that. Problem with that is it is usually only applicable to that specific data set. If we got the data from operating condition A, B, and C, and those conditions now change to D, B, and C, then that model is not necessarily applicable anymore, because we changed one of our inputs or something like that, and now that model might be completely bogus, and we need to develop a new model for us to explain our behavior of our process. Then lastly, the combination of the two, which is semi-empirical models. So semi-empirical models contain some form of fundamental principle development, but also some form of data from known systems or from an existing system that you have. And these are typically the models that we use most often in industry. They are kind of a compromise between your perfect ideal theoretical model and the somewhat disadvantageous empirical model. So you take the best of both worlds, combine them, and you end up with a semi-empirical model. Not 100% accurate always, but we as engineers like to believe that 5 to 10% accuracy is okay-ish. Right, I think, okay, yeah. It is way too late to start with this now. But we will continue with this blending system and derive our first dynamic model for this in tomorrow's lecture. I hope you enjoyed this lecture. If you have any comments or suggestions, please do let me know on Slack. I would very much like to get your input. And I shall see you this afternoon at 2:30 for the tutorial session. Thank you very much, and enjoy the rest of the morning.